Good afternoon, everybody. It is my pleasure to welcome Ram back to MSR today. Ram is not a stranger to us. He spent his last summer in ASI as an intern working with us on the intersection of perception and reasoning and how we may able to train deep learning systems for consistency in their reasoning problems. I think you are going to be mentioning some of that today as well. Ram is finishing his PhD at Georgia Tech, where he is advised by Devi Pari. Some of us know her pretty well. And his work is at the intersection of interpretability, deep learning, vision-to-language systems. And I'm looking forward to what Ram is going to talk about today. So.
Thank you so much for the wonderful introduction, AJ, and also for the wonderful time I had here at MSR last summer. Today I'm going to be talking about my work on explaining decisions made by deep models and how we can use these explanations to understand when models are biased and improve or correct them through some kind of a human feedback. So this is a story that many of you might have heard at some point of time. So in the 1980s, apparently, the Pentagon wanted to harness computer vision technology to detect camouflage enemy tanks. And so the research team went ahead and collected a bunch of images of tanks hiding behind trees and just trees which had no tanks behind them. And they implemented a machine learning model that actually gave a very good accuracy. So but then later they found out that this model was actually right for the wrong reasons. Basically, it turned out that all the images of tanks were taken on a cloudy day, while the images of the trees were taken on a sunny day. So the model had been asked to learn to separate the two groups of images, and it chose the most obvious way to do it, not by looking at the camouflaged enemy tank hiding behind the tree, but by merely looking at the color of the sky. If there existed some tools that could have told them where the model was looking at, then they could have saved them a lot of embarrassment, right? And it looks like people have thought about this problem for a really long time. But why do we care about this problem right now? Until recently, these machines were not in a state where we could use them in real life directly. But we are inching very close to scenarios where these machines are going to make decisions for us. We are inching closer towards a reality where fully autonomous systems are going to transport us to work every day. But when such cars fail, they fail spectacularly, disgracefully, leaving an end user look at some kind of an incoherent output, wondering why the car did what it did. Right, and unfortunately, we currently live in a world where machine learning based mistakes gain much more attention than human made mistakes, right? And very soon these machines would be assisting doctors in performing surgeries, and if the model suggests something out of ordinary, we wouldn't know if performing that would lead to some kind of a catastrophic failure, or is it just something that we have not yet explored. And even legally, with the introduction of GDPR, we are headed in directions where these machines we have to build machines that explain their decisions to any user. Right, so in this talk, I'll first be talking about my work on explaining decisions from deep networks. This is my ICCV 17 and RGCV 19 paper called Grad-CAM. Next, I'll be talking about how we can use these insights to understand insights gained from these explanations to understand when models are biased and debias them. Following that, I'm going to be talking about my work on my recent work on how we can use human explanations to improve the reasoning capabilities of models, and finally discuss some future directions that excite me. So coming to the first part, the question I wanted to ask was, how can we explain decisions from deep networks? And let's break this down. What do we mean by the term explain? So visual explanations, at least in the sense of vision models, we are asking the question, where does an intelligent system look when it's making a decision? And let's combine this with the next term, explaining decisions from deep models. And back in 2016-17, when I started working on this problem, there only existed a handful of approaches to do visual explanations. There were gradient-based methods such as backprop, deconvolution, guided backpropagation, and layer-wise relevance propagation. But then all these kind of approaches suffered from the fact that they were either noisy or not class discriminative. And I'll talk about what I mean by that in the next slide. And there were some works that achieved explanations or interpretability by simplifying the model architecture, such as CAM. But the problem is that these kind of approaches are only applicable to a very limited set of architectures. And you lose performance when doing this. There existed the very popular technique called LIME. During that time, it was introduced by Marco, who is actually working here. And this suffers from the problem that it does not take into account the parameters of the model, so it's model agnostic. So the problem with an explanation technique that is not model specific is that it will not be able to provide any feedback to the model with this kind of explanations that I'm going to be talking about in the second and third part of my talk. So coming back to the problems with existing approaches, if you take an input image like this and you do backprop, you get a visualization like this. And when you do decon, you get a very noisy visualization. And there were some works that try to address this noisiness factor. This was work called guided backprop. So if you have an image like that, we can see that there are two categories here. Now, if we do guided backprop for the category cat, this is the visualization that you get. Now, when you do guided backprop for the category dog, you get a very similar visualization. Even though the model has learned to distinguish the two kinds of categories, the visualization does not seem to capture that. That brings us to the question, why is explaining deep models particularly hard? So linear models with interpretable and maybe normalized features are of course interpretable because the weights corresponding to these features signify the importance. But deep networks are highly nonlinear piece of functions, so it's hard to estimate the feature importance for these deep networks. So before getting into how we can estimate feature importance, let's look at features at which layer actually make more sense to compute the importance. This is a typical network. You have a CNN that maybe classification CNN would give you a probability distribution over the classes that you're trained it for. Breaking this down, you might start with a convolutional and a ReLU layer, and then you might have some pooling layers, and then you have a bunch of these concatenated, and then finally a couple of fully connected layers that predicts the category. But what do these individual layers actually learn? So if you go back and visualize the filter maps of these individual layers, you can see that they actually look for edges or blobs. And these are not very interpretable. Right, and this is what earlier works like decon also found, that earlier layers the features actually look at edges or blob features. And so the defining importance in terms of first layer filters might not be very meaningful. Now, coming to the higher layers of the network, we find that, you can see that for this image, it seems to capture those dog regions, cat regions, striped maybe, and then the heads of the cat and so on. So you can see that these kind of later layers seem to capture more semantic information. They look for human-like regions. And so defining importance in terms of later layer neurons would probably make more sense. And now how do we determine neuron importance for these higher layers? Right. Let's say the model had a distribution over cat, dog, and bike, and this is what the model predicted for this image. Now we are looking to perturb these semantic neurons. So essentially we're asking the question, which neuron, if I alter, would make the model believe in the decision even more? Right? That's basically perturbations. You can add a certain small value and see how it actually affects the decision. So basically some kind of sensitivity analysis. Right? And you do this for each of the neuron, and you get a sense of importance corresponding to these individual neurons. And this is essentially the gradient information. This is what gradient provides us. Now, this is exactly the motivation for Grad-CAM. So what is Grad-CAM? Given an image, we feed it through the convolutional layers of a CNN, and we get feature activation maps. And you can use these activation maps for any task. Let's take the case of image classification task, where you have a couple of fully connected layers followed by a final softmax. And let's say this model predicted for this image that it's a tiger cat. Now, we are asking the question, which neurons are most important for predicting this category tiger cat? And we do that by computing the gradient corresponding to the score of tiger cat with respect to the last convolutional layer neurons. And this gives a gradient map which is of the same dimension as your feature activations. Now we do a global average pooling here to determine what is the weight of, to get a sense of how important every neuron in the last convolution layer is. And so in order to explain this particular image, we can now combine these neuron importances with the feature activation maps. We just do a weighted sum to get Grad-CAM. And you can see that this Grad-CAM is somewhat like a saliency map. Red indicates that the existence of the category where the model thinks it has to look when it has to make that decision. And you can see that it gives a sense of, it highlights the cat regions for predicting tiger cat. And of course, you can do this for any kind of task, right? You could have, like, say, an LSTM or an RNN that predicts the caption of cat laying on the ground. And then you can do the same thing. Or you can have additional input modalities, like in the case of visual question answering. Basically, you can do this for anything where you can compute gradients with respect to the score of the class that you care about. So since we train these networks with gradients, so of course this is fairly applicable to any task that uses a CNN. Yes?
Correct. If you say that, for instance, to generate cat, you have a softmax probabilities over the old vocabulary, and you get one that is corresponding with the cat, and you take the gradient with respect to that probability all the way to the pixel.
No, till the last convolutional layer.
Till last convolutional.
Last convolutional layer, because that is what is the most semantic, and that gives more human interpretable visualizations. So if you compute it all the way to the input pixels, you get very noisy vectors like we saw earlier. Yeah. And we can combine this with other approaches like guided backprop to get a more high resolution visualization that highlights these regions. And note that for this particular variety of cat, tiger cat, it seems to highlight the stripes more, indicating that the stripes are most important for this particular variety of cat. And you can actually visualize any decision, right? Like even if the model did not make this prediction, let's say the model predicted boxer. When you compute the gradients with respect to boxer, you get the importance corresponding to the category boxer, and now you get a visualization that actually looks at the dog. So I wanted to highlight some advantages of advantages of Grad-CAM over other methods that actually existed before we came up with Grad-CAM. Here we can visualize important qualities along these axes, right? Here you have axis that determines if the visualization is class discriminative, whether it's faithful, whether is it a function of the model, and how applicable is it. So if you take works like guided backprop and deconv, they fall in this category. Right? They are widely applicable and for a variety of CNN architectures, but they are not faithful or class discriminative. Works like Blime, they are, of course, widely applicable to a variety of architectures and class discriminative, but they are not, they are model agnostic, and so they lie there. And this was also the case for some generalizations like shape that Scott came up with after this. And if you see CAM actually is class discriminative and like function of the model, but it's not applicable to a variety of architectures. And whereas Grad-CAM is both model specific and is class discriminative and is widely applicable to any CNN architecture. And in addition to this, since you're only doing a single forward pass and a partial backward pass, it's very fast to compute as well. So, so during that time, not only were the visualizations somewhat fairly new, there didn't exist many ways to evaluate these visualizations. So we came up with these evaluations along these following lines. How interpretable is the visualization, the explanation? How faithful are the explanations to the underlying model? And can visualizations help user build trust in the model? Right. And to answer the first question, so we just gave images like this to users in Mechanical Turk and asked the question, what do they see? And what we find is that this shows that Grad-CAM is class discriminative. So just based on the visualization, people are able to understand which class is being visualized. And in order to evaluate faithfulness, we can compare it with by occluding patches of input image and see how that affects the decision. Like essentially, you could like put blocks here at each pixel location and get a map like this. And note that this is actually very expensive to compute. Like you do like 1 million forward passes to blocking each regions in the pixel and then get this map. But we can do this for a few images and compare it with Grad-CAM. And so what we find is that Grad-CAM portrays the model more accurately. And then to see if visualizations help build it.
Those numbers, are they, how do you calculate them?
There's just simple rank correlation between these vectors. So you will have a 224 by 224 map corresponding to the ground truth. The ground truth here is coming from the occlusion, and then you have what Grad-CAM gives, and you can do rank correlation between these values. This will give sense. So for this, what we did was we took two models, one like AlexNet and VGGNet, and then created visualizations for these two. We took instances where both AlexNet and VGG gave the same prediction, and then we showed users the visualization and asked which one do they trust more. And what we find is that Grad-CAM helps users place higher trust in a model that actually generalizes better. So this shows that even though two models make identical predictions, through Grad-CAM we are able to understand which model is actually better, which will generalize better. So after we released the paper, other papers probed more and created more metrics to evaluate saliency maps. And this was one popular paper from Beancam's lab that did parameter randomization tests and data randomization tests and found that among all the approaches that they evaluated, only Grad-CAM and Backprop satisfied all the sanity checks. So, so here are some insights that we gained when we did Grad-CAM. Given an image like this, the model often captions, we took the most simplest model, one of the first neural network-based captioning model. This model gave the caption a group of people flying kites on a beach. And you can see that the visualization actually highlights a little bit of the people and the kites. And here, a man is sitting at a table with a pizza, and it looks more at the man and a little bit at the pizza. And you can see that the word table is here, but then the visualization does not seem to highlight much of the table, indicating that these might be some words that just the language model took over and just generated that. And you can do this for VQA models where the task is given an image and a natural language question like what is the person hitting. The model seems to look at the ball and uses a little bit of the context, tennis court, to answer tennis ball. And what we find is that even simple non-attention based CNN and LSTM models somewhat tend to look at appropriate regions. So that was an interesting finding during that time. And we can use Grad-CAM to understand failure modes. Like when models fail, why do they fail? So for this image, the model incorrectly predicted this as a car mirror. And if we see the visualization for car mirror, it actually just highlights the mirror-like regions. And of course, you can now change it to predict the category volcano, and it looks right at the middle. And here, in this case, the model predicted this to be a wine snake. And if you see why it did it, it just highlights this region, and this actually looks like the wine snake. And you can do the same thing for the ground truth category coil as well. So this says that even unreasonable predictions sometimes have reasonable explanations. And we have a demo that is hosted here. Unfortunately, I'll not have the time to go through the demo, but then it is available online, and you can upload any image for any of the 3 tasks that I described and make and get the visualizations in very quick time. And after we released our code to the community, there's been a bunch of re-implementations of Grad-CAM in various frameworks, and in fact, that is in MATLAB as well. In fact, through Captum, like if you actually install PyTorch, the recent PyTorch, you will have Grad-CAM implemented there already, and same goes with TensorFlow as well through TF-Explain. And with over 1,600 citations, it's been very exciting to see how the community has been using Grad-CAM. They've been using it for a variety of tasks, both to show that their model actually does perform well, and also as some kind of a diagnostic tool to understand what it's doing. And like I found these extensions to be pretty interesting. This was Grad-CAM extended for videos. You can see that the class was called uncovering something. And you can see that the model places importance on the top even before it has been uncovered. So that's interesting. And similarly here for the class pushing, like you can see that as the person's hand comes here, the model seems to highlight the edge. And there have been extensions to text as well. Through Grad-CAM, people have found that words like fine, excellent, relaxed indicate positive connotation, whereas gone or tired indicate negative connotations. So, back in 2017 when I finished this, and I was hired by Facebook to apply Grad-CAM in a bunch of vision models, and as a result of that, Grad-CAM runs in the images that are uploaded in the back end, and researchers try to make sense out of their models. And last semester when I was interning at Microsoft, I also came to know that a similar tool exists at Microsoft as well. And of course, it has its own limitations. So if you give an image like this and a category, say cat, this is what the visual Grad-CAM would tell us. But then it's hard to understand what is the concept that is actually being represented by the pixels below. Or rather, how are these concepts actually used by the model? Right, so that's one limitation of Grad-CAM. So to summarize, in this section I talked about Grad-CAM, a way to interpret decisions from any deep network, and we found some interesting findings and impact that it had at various places, and some ways to evaluate these. So far, we have seen how we can use Grad-CAM to interpret model decisions. Now I'll talk about how we can use these explanations to understand biases in models and debias them. Any questions until this point? Mm-hmm.
So Ram, you have applied it in image captioning, VQA, and these are domains where the output has a very high cardinality, in that there might be so many captions that can be phrased in similar ways and they are basically the same. Have you thought about, how consistent are the explanations when you move into like these different ways of phrasing the same answer? Like yes, certainly, sure.
Certainly. I think like when we did this, we found that for several captions, some of the words are generated solely by the language model, and so they don't have grounding. So essentially, that says that I am like as a model, I'm just saying this certain words because I saw a bunch of correlations. When I saw a man sitting, I always saw at the table, so I just put that. There is no incentive for me to look at the table when I'm captioning table. So those kind of systems might fail, and that's exactly what I'm addressing in the next part of work.
It could be like a measure for
exactly
estimating how good the answer is.
Exactly. So now we have a tool to understand decisions from deep networks. Can we use it to improve the networks? So here is a riddle that some of you might have seen it already. If you have not seen it, maybe let's do this. So a man and his son are in a terrible accident and are rushed to a hospital in critical care. The doctor looks at the boy and exclaims, "I can't operate on this boy, he's my son. How could this be?" So this was a study that was conducted in Boston University, and so many people actually overlook the fact that the doctor is actually a woman, right? And so this kind of bias actually exists in real-world data sets, right? Female doctors are called female doctors, and male doctors are just simply called doctors. Right, so and AI models actually trained to do some tasks. They also capture the same kind of bias, right? We trained a model on data from a search engine, and applying Grad-CAM, we found that it did capture the gender bias, basically looking at the face of the person when saying nurse. And here it looked at the face and it actually answered it incorrectly. So what we find is that the models also learn to capture the same gender stereotype that exists in the data. And of course, by fixing the bias, you can fixing the bias that exists in the training set, essentially making sure 50% of doctors are male, 50% of doctors are female. This fixes the model, right? So essentially, the model now makes the correct predictions and looks at appropriate regions. But is this balancing data set possible in real life, right? Reducing biases in training set is not an option in real world data sets, right? We don't even know what kind of bias exists. And even if we know what bias exists, we can't go back to our training set and see how each example is biased. And if we still do that, the model might learn to capture a different kind of bias. And so it's very hard to do. Right, and this is even more problematic in vision and language models, as models tend to use statistical correlations to arrive at their decisions. Right, the model might often caption this as a giraffe standing next to a tree, even though there is no tree in the image, because most images of giraffes in the training set occur with a tree. And for the question, what color are bananas, models often answer yellow. And if you see in the training set, most images of banana are yellow. And this is especially problematic when distributions change. Right? When the priors that you expected to see, that you saw in the training set, no longer hold in the test set, these models which don't ground the decisions correctly are going to fail. So I wanted to see if interpretability can help in some way. So until now, people are only using interpretability to establish trust, but I wanted to see if we can do something more. So in this work, I was trying to answer the question, how can explanations help unbiased AI models? Right, so this is a popular architecture that was introduced in 2017 called the bottom-up, top-down architecture that many of the models, vision and language models these days also use. And we applied our approach here. So given an image and a question like what room is this, it just converts into a bunch of region proposals and then does some kind of attention and some computation over that. And then you have a couple of fully connected layers that gives you the answer. For this particular image and question, the model answered dining room. What room is this? It thought this was a dining room. Now, through Grad-CAM, for the correct answer, kitchen, we can understand where the model was looking at. And what we find is that the model was looking more at this region than at the regions you would think matter more. It was looking at the dining table, not at the stove or the microwave or the fridge. Now, can we fix this model? Right? So, but typically, where do humans look? Right? This was data set collected earlier from our lab called the VQA hat data set. People were given a question and a blurred image, and people had to unblur the regions that they think are important. And so you get a visualization like this. So essentially, you now get a sense of where humans look at in making decisions. And this is available only for a very small percentage of the VQA data set. So we can use this data set to understand, you can understand how much individual proposals are important, and you get a sense that humans typically tend to look at the microwave or the stove or the fridge. Now we introduce an approach called HINT, Human Importance Aware Network Theory. So essentially the idea is to make machines look at the same regions as humans do. So now we know where machines look. Through this data set, we know where humans look. Now can we add some kind of a ranking loss? Thank you. So now you can introduce some kind of a ranking loss, and this ranking loss will enforce the machine's the importance should match the human importance. And so essentially, you train this model until convergence, and so essentially the machine importance now matches the human importance. Essentially, one thing to note is that this Grad-CAM is a function of these highlighted parameters of the model. Yeah.
So can you say a few things about how this data set is collected?
Yeah.
Is it aligned, like human, like same image, human? Can you say more?
Yeah. So the way this data set was collected was, this was the interface that people were given. Okay. And there was a question, what room is this? And people were given this interface, and they were given a mouse pointer, and basically they can, like when I look at this image, I see that there is some object somewhere here. So it might make sense for me to deblur and see what that object is so I can answer this. So what they do, So what they do is, like when you unblur, you get a heat map like this. And similarly,
More clear, so it's more like
yeah, it's just deblurring.
Okay.
Yeah, it's exactly that. And now we get this, we know where humans look at for answering this question. And in this we know where machines look at, and then we impose a ranking loss. And Grad-CAM is a function of these model parameters. And if you want to make this thing look similar to humans, all the network parameters until that point have to be updated. And that's how the model is getting updated. So coming to results, what we find is that applying this, especially when distributions change, we get about a 7% improvement in VQA performance. And a small improvement in the general VQA sense too. So what this says is that making machines look at regions similar to humans makes them generalize to arbitrary distributions better. So did you have a question?
It seems like a low base, 39%. Isn't that quite low?
Oh yeah, that is a wonderful question. So this is the data set where prior distribution, the training set, the priors that exist in the training set do not exist in the transfer over to the test set. So
is VQA CP.
Yeah, this is the VQA CP.
Oh, I see. Okay, right.
Yeah, exactly. So models which don't ground this better will not be able to perform good in this task. And of course we went ahead and implemented this for image captioning as well. So this is fairly straightforward approach that you can apply to any kind of model. This was a model that for this caption, a bathroom sink with a toothbrush, soap dispenser, and mirror. When generating the word toothbrush, this model was looking at these regions. So basically, it was using more of the context to say toothbrush. But after applying hint, we find that now the model only looks at the toothbrush. And here is an interesting example where for the class of a woman with a tennis racket with a cat in the air, the cat actually, after applying hint, you can see that Grad-CAM now highlights the cat, which is not actually a cat, it's actually the shadow of the cat. The cat is actually somewhere here. So yeah, but of course this has its own limitations, right? Human attention can be somewhat misleading. If I give you an image like this and ask what color is the sky, you might just unblur this region and say, okay, the sky is gray. But then making machines look at these regions and not any other thing might make the models get confused, right? So that's one limitation. So there is a lot of work that has to be done to understand what is the exact kind of human supervision that we need to provide these models. That's an interesting line of work. And so in some cases, it's actually not even clear what regions are important, right? If I give an image like this and the question, are the man and the woman together? Like, what is the human attention here, right? What is it? Is it the, what about this region is actually important? Right, so visual attention is not very sufficient, right? So there is a need for deeper understanding beyond what is visually present. So whereas with natural language, I can be like, the man and the woman are not together because, say, their paths are actually diverging, or they are not holding hands, or the distance between them is not small, and so on. So that's exactly what I do in my next work, where we try to understand in the other modality how these models reason. Yeah.
So this is actually quite surprising to me in the sense of, so we know from studying the human visual system that oftentimes identification of an object in the scene relies more on a snapshot of the scene's background than the actual object itself to kind of ground human perception in the context of the scene. And so I'm actually quite surprised to see that when you fine-tune with that on your deep network, that you actually focus on the object. Do you have an idea why that might be the case?
So what we find is that initially, sometimes models don't seem to look at the right regions that they should look at. And I think, especially in data sets where you expect improvement only if the model is actually looking at the right things, like in what color is the banana, if I just say banana color, always yellow, it's going to fail. But if the distributions change, only if I look at the banana, I'll be able to answer it, right? So forcing models to look at the banana when answering the color about the banana is what makes these models right for right reasons. Yeah, so to summarize, we saw that models are typically biased, and they tend to make decisions based on statistical correlations that exist in the training data. So we introduced hint, a way to make models look at regions similar to humans, makes them generalize to arbitrary distributions better. And yeah, any questions until this point? Okay. So far I talked about how we can explain decisions from deep networks and how we can use these explanations to understand when models are biased and make them look at appropriate regions, thereby debiasing them. And now we have seen how visual explanations sometimes might not be sufficient, and there is a need for deeper understanding of context regarding how humans reason that go beyond the content in the image. So in this work, I'm going to be talking about how we can enable human-like compositional reasoning through an approach called Squint. The question that I wanted to address is, can models benefit from human-like compositional reasoning? This was work done here at MSR last summer with AJ, Bessa, Marco, and Eric. So there's been a lot of use cases that we can think for VQA, right? One could be to help the visually impaired folks. You can have an image and you can have a user click an image such as this and ask the question, is the banana ripe enough for me to eat? The model might say yes. Okay, you're happy, but you want to probe more. You want to understand, is it right for the right reasons? Now you ask the question, just to be sure, you're asking, is the banana mostly green or yellow? And now the model says green. You're like, wait, what's going on here? Right? So the model seemed to have gotten the more complicated reasoning question right, but simpler question wrong. It could be for when you're situationally blind, where you send a robot to aid with evacuation, and you ask, is there an emergency? It says no. And you have a bunch of other questions just to be safe. You ask, is the room on fire? Is there a lot of smoke? Are there a lot of people? It says yes. So this makes us think about how do humans typically reason, right? If I am given an image like this, and the question is, the banana ripe enough for me to eat? I would typically think that, okay, ripeness in case of bananas is actually referred to by the color of the banana. And now I ask myself the question, what color is the banana? And based on the fact that it is yellow, now I answer yes to this question. But how do we train current VQA models? Typically, we just feed in all these questions are actually treated equally. We just feed all these questions randomly without any regard to complexity or common sense requirement. We treat questions like what color are the man's shirt, and a more complicated question like, is this a good idea for a rainy day, all the same, right? That does not make sense. And after doing this, we expect the models to learn compositionality. So that's the problem here. So there is a need to first classify these questions based on complexity, right? In VQA, you could have an image like this and a very simple question asking about the color of the couch, basically a physical property. And more complicated questions like, do they look relaxed? Questions like, say, is there a fork? Versus, could you pick up this pizza to eat it? There could be questions like counts, right? How many bears are there? 2. And questions like, was this picture taken in Australia? Right? Or questions asking about spatial relations of what is right of the plate. I ask whether it's breakfast, lunch, or dinner. Here the model has to learn that there is sunlight hitting, and it's a sandwich, so probably sunlight would indicate it's either lunch or dinner, breakfast or lunch, and the fact that it's a sandwich, people don't typically eat sandwich for breakfast, so it's probably lunch. Right, and things like requiring you to look at the signs. So what does the sign say? Stop, versus questions like, is it going to rain here? So if you can see, the left set of questions are perception questions, and the right set of these questions are reasoning questions. Right, so basically we make this categorization. We divide the dataset, VQA dataset, into perception and reasoning questions by a bunch of hand-labeled rules. And then we create a sub-VQA. We collect a new dataset to obtain perceptual evidence for these complex reasoning questions. We collected this dataset on Mechanical Turk. So this is how our dataset actually looks. If we have a question like, is this a keepsake photo? You might have perception sub-questions like, is this a black and white photo? Is the woman wearing white veil? And is she holding flowers? And what is the man wearing? And so on. Here, for the question, is this giraffe at the zoo? People typically tend to ask about the existence of a fence, about the grass, and so on. And here, for the question, does this appear to be an emergency? People typically talk, for this image, people talk about the existence of ambulances, fire trucks, or a lot of people gathered in the middle of the road. And here, is this a good idea for any day? People typically talk about the roof that exists in the vehicle. As you can see here, in this data set, we have the main question and a bunch of these sub-questions, which are definitely lower level, but talk about the perceptual evidence that exists in the image and are required for answering the main question. So how can this data set help? So for evaluation, we can ask the question, do current models reason compositionally? And basically, are they consistent? And in order to improve models, we can ask the question, does human-like compositional reasoning actually help current models reason better? Right? So for the first one, so in order to ask if machines reason compositionally and basically how consistent our state-of-the-art approach is, for the in our data set, what we find is that basically we can divide this into 4 quadrants, right? Where the main question is answered correctly, but the perception question is answered correctly, and then you can have cases where the perception question is answered correctly, but the reasoning question is not. And similarly here, both are answered incorrectly. So essentially, you can divide the space into 4 quadrants. And what we find is that about 28% of the times, the model is right for the wrong reasons. So, meaning it answered the main question right, but the perception question incorrect, indicating that it was not using the right kind of reasons to arrive at the main answer. And so, the second question that we are asking is, does human-like compositional reasoning, does that help current models? Right, so the question is, does making models use the right perception concepts make them reason better? Like if teaching people that in order to answer this, you need to focus on this question, does this help current models? So we introduced this approach called SQUINT, sub-question importance aware network tuning, where we have an image like this, and the question, what season is this? So we can see that in order to answer this, it's actually you need to attend to these regions like the Christmas tree, right? So this, and we can now understand where the model was looking at for the main question. Now we know where the model was looking at for the sub-question. Now we provide an attention loss that encourages the model to look at the same regions for the main and the sub-question, and also answer the sub-question right. And then we have a loss for that, and then we have another loss to make sure that the model answers the main question right. So essentially, this is what the model does. It makes the attention for the main question similar to the sub-question, and makes the model answer both the main and the sub-question correctly. So how does this do? So now we have these 4 quadrants, and then the reasoning accuracy, which is essentially the combination of these 2, and then consistency that we talked about. How many times is the model right for the right reasons? That's consistency. And what we find is that the model, this is what we saw before. We observe a small improvement in the reasoning performance and a big improvement in the consistency performance by applying SQUINT. So showing that making human-like compositional reasoning can help machines reason somewhat better and be more consistent. Yeah. So the next question, do squinted models actually look at the right regions? So if you take an image like this, and the main question was, is this clock in America? Right, and the model actually initially answered no. And you can see it was just looking at the clock. Even though the question is about the clock, it's about, like, you need to focus on the existence of the flag, right? And if you see here, the sub-question was, is there an American flag? The model answered yes to that and was looking at the flag. Right? Now, if we make, so this is basically a reasoning failure, right? It got the perception concept right, but it didn't know that I have to use that perception concept to arrive at the answer to the main reasoning question. Now, so making the machines look at this particular region when answering this question, what that does is now the model not only answers this question correctly, but also looks at the American flag, the correct regions. And so what this shows is that we can correct reasoning failures through SQUINT. So to summarize, in this work, we created...
So for this line of work, you know, you are doing this joint training between perception and reasoning questions. And there is an improvement in consistency, but the reasoning improvement doesn't improve that much. What do you think we need to do more so that you can actually have bigger jumps in reasoning, in perception, overall, the overall performance of the system improves?
Yeah, I think one assumption that we made is that the perception concepts are captured correctly. And now we are forcing the models to reason on top of the correct perceptual concepts. That is an assumption that is not verified, right? So if we combine works like Hint, where we make sure that the perceptual concepts are attended correctly, that kind of thing would help these models as well, because we are now assuming that always the perception, where the model looks at for answering the perception questions are right, and reasoning on top of that would make sense. But if that is something that we need to look at. Yeah, so to summarize, in this work we created a new data set of sub-questions. We first introduced a new split of reasoning versus perception, and then we introduced a new sub-VQA data set. And we can use that to evaluate and enforce compositionality in current models. And we saw how Squint could be a first step towards how human-like compositional reasoning could help improve VQA performance on more complex tasks and complex questions. So until now, we have seen that I looked into how we can explain decisions from models and use these explanations to correct these models through some kind of a human feedback. And now I want to talk about some future directions. I wanted to divide this into some immediate future steps and then some long-term steps. So coming to the immediate steps. So modality-specific explanations. What I mean by that is, say in VQA, until now we have only been focusing on explaining decisions in the image space, right? But there is another modality, the text, that we are missing. Right, so having an interpretability approach that can explain both these modalities would make us understand the model better and give appropriate feedback. So imagine a system where is this for this question, is this clock in America? The model not only gives you an answer, but also generates a bunch of questions that it was using to arrive at the answer to the main question. Okay, so that way we can understand the model better as to why it's doing what it's doing. So what can we do with that? So we can provide some intuitive ways to fix these models, right? So we can ask the question, can fixing the answer to the main question fix to the generated sub-question, does it fix the model? What I mean by that is, if we have an image like this and the question, will the batter hit the ball? You can see that, let's say the model actually incorrectly answered this as yes. The answer to this question actually is no, because the ball passed the bat, right? Let's say this system came up with these questions. Is the batter looking at the ball? And it's the ball in front of the bat. First thing, you can see that it's good that the model is asking the right questions to itself. And so that's good. But then here, is the ball in front of the bat? It actually answers yes, where the answer is no. The ball is not in front of the bat. Now, if a human can go ahead and fix these models, fix the answer to the generated question, does the model now answer the main question correctly? So this helps us understand why the model is doing what it's doing in much more intuitive ways, and we can understand what's going on. Now, the other direction that I'm very excited about is how to incorporate domain knowledge, human domain knowledge, or rules into these deep networks. It's always hard to specify the exact goal for any machine learning model, right? So we need interpretability to close the gap between misspecified and the actual goal that we want. So paired examples are often an indirect way in which we try to feed domain knowledge to an AI and hope that it will learn what we want it to. But paired data is often not sufficient to capture the domain knowledge, right? So in most cases, it's not possible to provide to basically capture all the kinds of nuances that that are associated with domain knowledge. So this system would have to be dynamic and evolving. Right? So we need to move beyond just feeding models just trained data. If there is some other additional feedback that we can provide about what about these examples, does that generalize better? Do these kind of models now use less data and are right for the right reasons? So essentially, if we can convey to a model domain knowledge in its most natural form, right? If for this, if I can tell a robot that for predicting the class nurse, do not focus on the gender, right? So how like designing systems that can take feedback in the form of natural language and fix themselves. That's a direction that I'm very interested in. So in my ACCV 2018 paper, I looked at how interpretability can serve as a medium to incorporate domain knowledge, human domain knowledge in the form of natural language to basically extend classify to detect new classes. This is, of course, a first step towards incorporating this human domain knowledge through a different modality. But in the future, I think we can build on this to do a lot more interesting things. So coming to like how I think interpretability will play a role in the future of AI, I think we can divide, we can see 3 different stages of AI evolution, right? First, when an AI is actually significantly worse than a human, say VQA or things like that, where the goal could be to identify failure modes in these systems. And what that can help us do is help the researchers focus their efforts on specific modules that would lead to the good improvements. And 2, when an AI is actually as good as a human, like it's actually ready to be deployed, right? So, say image classification trained on a bunch of data. The goal could be to help establish appropriate rules and confidence in users. And when an AI is actually better than a human, maybe like say in AlphaGo, in the game of Go, so we could like teach, these machines can actually teach humans as to how to make decisions, right? So machine teaching where a human can know how to make better decisions through these interpretability approaches. So given like in future, I envision a system where given a model, a user would be able to provide targeted feedback in any form, and the model should keep everything the same and only update the part of it that are required to cater to the user specification. And if it's not going to be the case, maybe it can now tell us in much more interpretable ways why it cannot do what we want it to do. So we can adjust the way we provide feedbacks to these networks. So basically a future where humans can exactly specify in any form what the model should be doing, and we get a model to do that. So to summarize, I have worked on explaining deep networks and have looked into how we can use these explanations to debias or understand models and debias them when they are biased, and looked at how we can use these explanations to correct these systems and make them more robust and consistent. And I'll discuss some future work directions. Thank you. Thank you.
Any questions for me? I'll ask one. A lot of these consistency checks and improvement steps actually assume that the machine should be thinking, perceiving, reasoning like a human. Because, the idea is humans are doing it this way. For you to be robust, for you to be generalizable, this is how you should be reasoning as well. Do you think there are some limits to this kind of human consistency checks or this kind of human input in terms of how much the AI systems can get?
Certainly. I think, yes, I think it, of course, there are limitations, mainly because we as humans assume that we do the things in the most ideal ways, but that might not be the case. And we have systems like Go, which actually beats humans and are actually much better than humans. So what I think is, until we have a system that can outperform us in like several aspects, these machines still have some way to benefit from human feedback. If we don't, so essentially if the machine is already good, like we actually don't know how, say, planes fly, right? But we are not afraid to sit in a plane, right? So things like that, right? Like if you can guarantee me that this model is working the best it can in almost all scenarios, I don't care about these explanations or like some ways to provide human feedback is not very useful, right? Because already the model is good. Yeah.
I'm curious about the trade-off between leading the reasoning procedure for a model and the ability of ML models to pick up on clues that humans either aren't aware of or can't enumerate.
Yeah.
And if the more we lead them, does that mean that we give up their ability to handle circumstances that we didn't anticipate?
Yeah, I think like anytime you are actually feeding in models just with the rules, right? These machines are gonna not perform very well when when we specify rules, we make some certain assumptions. That assumptions might not be true for the model, right? So it is important it's a feedback process, right? It's a human in the loop. If the model does not do what I wanted it to do, now if the model can actually tell me why that is the case, like through interpretable ways, that's what is going to make me now give a better kind of explanation that can help the model. Yeah, good question. Thank you.
So on the compositional reasoning, like in the current work in Squint, we don't assume any ordering between the sub-questions, in the sense that it's not that you have to answer one sub-question first and then the other one after that. I'm wondering if there are tasks where the ordering is actually important and you need to have these substructures where you condition on the previous one.
Yeah. So what we can do here is, in this case, like let's say in this scenario, we just add one sub-question, right? Let's say there are multiple questions that the model has to look at. One simple way to do is here, of course, the main question attention will remain. For the I'll have attentions from multiple questions. I want these attentions to now combine. Simply, I can add all these attentions, and now I want the main question attention to match the sum of all these sub-question attentions. So that's one way to incorporate information from other sub-questions, I think.
And there would be like conditioned sub-questions, in the sense that there would be like a chain of sub-questions.
Yeah, a chain of these sub-questions, and then you add all that information and then help the models do that. Yeah. So, hi.
Yeah, so within, I think, human visual studies, there's been inconsistencies found in like the software versus hardware of human brains, right? So if you look at fMRI studies of how human like neuronal level visual cortex things fire, they actually aren't even consistent with what the human reasoning layer seems to say. So for example, at attention scenes, what a person might verbally express as the focal point of attention is not actually what their brain is lighting up and saying what they're looking at, right? And so I'm wondering if you're aware of any work in the computer vision domain that touches on any of that.
Wonderful question. Actually, you're right. In the way, especially when humans are asked to come up with post-hoc explanations, they tend to be like, I think I would have made the decision for looking at these regions, but more trustworthy ways to get that information is very useful. Like say, in the context of a hint where we got human attention, if instead we attach humans with a gaze tracking system, and then now this is during the data collection stage itself, when people ask what room is this, these humans might we exactly know where they look at, basically like where they attend to, which regions do they look first, and then how their attention changes to a different region, what do they look there. So all that temporal structure in addition to the faithfulness that they are looking at these regions to answer this question. So that is not something that is done right now, but I think hooking people up with these gaze tracking systems, at least for when collecting vision data sets, is going to help quite a bit, because they are not doing anything in addition. It's just a system that they are set up with. I think that is going to help these machines a lot. In fact, this addresses one of the limitations that I talked about, right? What color is the sky? Like machines just, humans might just unblur some regions, but then if we know where exactly they looked at, probably we will have a better sense and provide focused feedback in a much more interesting way.
As part of your future work, do you think you will try to integrate with some sort of symbolic system to describe the ontologies, or do you think that neural networks are the best way to
Oh,
describe
wonderful
them?
question. I think there's something intermediate where you need to embed these individual neuron activations to say a certain symbolic concept. And like if we can do this mapping, and I think in fact we had tried to do this. Basically, we tried to automatically name individual neurons in a network, right? So basically, what do these later semantic neurons actually look for in the image? And what we can do with that kind of information is that we can now, when we say that, okay, if I can identify, say, gender as a combination of like male, female, and a bunch of those neurons, and now if I can give a rule that for the class nurse, don't focus on gender, now that gets mapped to these individual neurons now. So now we are all back in the neural space. Right, so now you do exactly what we're doing, like now making sure that when I feed in an image of a nurse, it does not use the gender part to answer, make this decision.
Thank you.
Okay, thanks, Ram, again for a great talk.
Thank you. Thanks for the wonderful questions.